to my AI lecture series today. And it's a real honor to have a special guest, to have Robin Rombach here. Robin has pioneered how we create images from text input. Obviously, everybody knows the famous latent diffusion paper. After a few years of publication, it now has over 15,000 citations, and it's pretty much become a standard right now in the academic community, how you create images, and generally speaking, how you use diffusion models. But Robin not only has made foundational impact in the academic community, he has also taken these works to industry. First, he joined Stability AI, where the famous Stable Diffusion was created. That is, well, still probably one of the state-of-the-art open source models that many people use. And recently, like last year, he started his own company, like Forest Lab, which is great because it's in Germany. And he has been leading the company as a CEO right now, and they have released Flux, which is the title here of the talk as well. So now I guess we're going to hear a little bit of the differences between flow matching and diffusion models today. So we're very honored to have such an esteemed speaker today, and it's really amazing to see so much great work from his and his team. So yeah, the stage is yours.
Awesome. Thank you so much. And great to be here. Big fan of your group and overall, what you're doing in Munich. And thanks for the intro. So I can basically skip my first slide here that I prepared. I will talk a little bit about latent diffusion still, just to put it into perspective, and because I still see a lot of discussions online around do we actually need latent diffusion? Can we do end-to-end learning, etc.? Maybe we can also have a small discussion in the end. What I also want to talk about is just in general the foundations of latent generative modeling. Latent diffusion is one instance of that. We have seen other approaches in the past, recently also integrated into Gemini 2, for example, with their native image generation, and also use autoregression in a latent space. Just want to give a little bit of a high-level motivation and a primer on why I think it's actually reasonable to do generative modeling in latent spaces. Then I will transition into Flux and its foundations, the foundations being flow matching and distillation. And I will talk about one particular aspect of distillation, which is adversarial distillation, which we have as a group developed over the past few years. And then, talk a little bit about the future and where I think this field might be headed. And very curious to also have a discussion about that. If you have any questions, please feel free to ask them right away. As Matthias actually also has already said, I'm working at a company currently called Black Forest Labs, which we started here in the southwest of Germany, in Freiburg. This is not a real picture. This is a sample generated by Flux, but it looks pretty close, so I thought I'd put it here. And this is a real picture. This is part of the team. We actually have to take a new one because we have grown quite a bit. And we are based both in Germany. We have another hub in San Francisco, which is growing, and then a few team members distributed around the world. And it's also something that in the end, if there's interest, happy to talk about some startup learnings that we've made in the past few months. What do? We develop, as Matthias has said in the intro, we develop generative foundation models. We have put out a series of models that's called Flux. And one instance of this model called FluxDev. It used to be the most popular on Hugging Face and also the fastest growing until very recently, when we were also hit by the DeepSeek moment. But I think that just means that our next model has to beat it again. In general, we have seen quite some impact from that model that we put out in August last year. And I want to use this talk to give a little bit of an overview and the foundations behind it. And I think before we do that, it might be interesting to just recap how quickly the space has evolved as a whole. So I personally saw a lot of the evolution during my PhD and my master thesis before when I started working on this stuff. But it started a bit earlier, 2014, with foundational papers on variation autoencoders and GANs, where yeah, we saw the first results on datasets like MNIST at, I don't know, I think 16 by 16 resolution, but still it worked. Then some low resolution, colorful images, 2016 Pixel CNN and related works. And then the first, I would say, more general and scalable approach, 2019 BQVA2. All of this was still like fairly restricted in that it was mostly class conditional synthesis. So you would give the model a label, like in this case here, the fisherman, and then it synthesizes, given that discrete label, an image. And this has, as we all know, evolved quite a bit. So today we have a bunch of models that are actually also used in products around content creation. I'm naming a few here, like Midjourney, DALL-E 3, Recraft. A recent one, which I find very impressive, is VO2 by Google, which is a video diffusion model and is able to produce like really impressive, realistic results. And of course, also our model Flux, which I want to talk a little bit more about today. So maybe to get into it, we can have a look at a few samples that are actually coming out of Flux, and just to emphasize again how much this has evolved from like the class conditional case. We can now generate in free text or prompt a model by free text and basically compose any image that we would want to. So in this case here, I gave the model a prompt. This is a blue ball on top of a red cube and a green triangle behind them. We have a dog on the left and a cat on the right. And it does exactly that. You can also play with the prompt a little bit and rearrange things, like putting a green ball on top of a blue cube and put that on top of a red triangle, and it still works. We can also add text to these generations and keep the composition. The results, just for like, I would say more random prompts, like walking by a river, they look very photorealistic by now, like a random snapshot that you would have taken on your iPhone maybe. And another aspect is that we're also seeing in production, which is quite a big use case, is spelling, where we can accurately describe stuff like logos or just imprints on general images. Like, for example, here on the struct that we have generated, and this entire image is generated. And a last piece that we can also now start to do more and more with these models is text-based editing. So we can take in an image and actually using a text prompt modify it and change it into something or customize it into something new. That will also be part of the outlook in the end, because I think it's a very exciting future direction. But let's go back a little bit and talk about how do we get there? How do these models actually achieve this very impressive quality? Of course, I'm going to say this is because of latent flow matching. There's like two different aspects here in this paradigm. One is the latent, and the other is the flow matching. Let's first focus a little bit on the former and recap what actually is latent generative modeling. So to kind of explain what I mean here, I made this slide. So we have two images here, which look very much the same. And perceptually, I would say they are the same. One is a JPEG compressed version on the left of the right-on image. And we see that the JPEG version is roughly 10x, or sorry, the PNG is roughly 10x the size of the JPEG. And of course, this is nothing new or fundamental. We all know image compression, but it kind of hints at the fact that for a human observer, what matters is perceptual realism and equivalence, and not really the last bit of detail that might be present in the actual signal. And we can visualize this here with I would say, qualitative plot. When we plot something like the perceptual similarity of an image and versus like an approximation of that image, such as a JPEG compressed version against the file size. And when we do this, we get a plot that conceptually looks quite like this. We see that perceptual similarity quickly increases to a high level and then kind of stays constant. This is basically what lossy compression algorithms like JPEG make use of. So the question is, what does this have to do with generative modeling? And I would say it has to do quite a lot with it. Again, this principle was, of course, well known before generative models really took off a few years ago. But I think we only found very recently, actually, like a good mapping into how do we represent a model that in actual neural networks or neural network architectures that we use to train these generative models. And yeah, this is basically just a conceptual overview of what latent diffusion and other latent generative modeling approaches do. So the idea is super simple. So we first train a compression model where we use an encoder that maps an image into a lower dimensional representation. And then we force it to kind of remove some of the information, both by the dimensionality reduction and also some regularization. This can either be a discrete bottleneck like vector quantization, or we force the latent distribution to follow a simple distribution like a standard normal. We then use a decoder to map that representation back into the pixel space. This model we train end-to-end with the task of reconstructing the input image as good as possible and in a, this is important, perceptually plausible way. And we achieve that by doing two things. One is it actually uses a so-called perceptual loss, such as LPIPs. And more importantly, it also uses a local discriminator on top of the reconstructed image. So it's actually not a pure autoencoder, it's a combination of an autoencoder and an adversarial network. And like this, we can actually obtain reconstructions that are perceptually pretty much equivalent to the input images. And this latent space that we obtain through this method is then much lower dimensional than the actual pixel space, because it contains only the perceptually relevant aspects of the input images and kind of removes these imperceptible details. And what it does, if we do this, is that we help a neural network that we then train in the second stage on the latent space in two ways. First, if we consider transformer architecture, the sequence length that we train on is much reduced. So that obviously helps to keep the whole training computational efficient. The second aspect is that we actually help the generative model itself. So if we consider the main classes of generative models, such as likelihood-based models here on the left and adversarial models on the right, we basically can distinguish between two different modes. One is, or two different classes of models. One is the more kind of mode covering models, likelihood-based models, such as standard autoregressive transformers, but also diffusion models. And the second one is the adversarial models. And the likelihood-based models, they have a lot of advantages, like stable training objectives, like based on cross entropy or regression losses. They're very easy to scale, but have one like large disadvantage, which is that they get lost in the details. And this is really because this objective really favors output distributions that cover the whole space. And if we would not remove these imperceptible details I was talking about earlier, then the model would be tasked to not only learn like the overall structure of images or the data, but also like all these details that we as human observers in the end do not really care about. And this is the second aspect beside the dimensionality reduction that we achieve through latent generative models or through the autoencoder that really helps this paradigm to work, which really makes like the whole latent generative approach scalable. So in a nutshell, we use adversarial models in the first stage, where we actually exploit the mode-seeking behavior with the added discriminator on the autoencoder. And then in the second stage, once we have removed the imperceptible details and reduced the dimensionality, we can use a likelihood-based model, such as an autoregressive model or a diffusion model into latent space. This can also be conceptualized as texture versus structure or stuff versus things. So, for example, in this image here, the stuff is the fur texture is very high entropy. And we, as human observers, we do not perceive individual realizations of this texture. We just perceive it as the concept fur. And again, this enables the autoencoder to drop a lot of the modes. So, for example, other realizations of the same texture, and to represent the presence of this texture more compactly in its latent space. And as I said, this makes then generative modeling easier. We can quickly look at one illustration of what happens when we turn on and off the adversarial loss and train these models. So on the left, we have the input image, and then we train two different models. One is a standard autoencoder without the adversarial objective. The other is with the adversarial objective added. The bottleneck size, the architecture all remains very much the same. It's just the fact that there is an adversarial component added to the overall loss. And we see that for the case with the standard autoencoder with just a regression objective, we have slightly blurry reconstructions because the optimal solution is kind of the mean of the different realizations. Whereas with the adversarial objective added, the reconstruction has to snap into one realistic mode of the image manifold. All right, so by now we have motivated what latent generative modeling is good for, why latent diffusion overall makes sense. So I can switch gears to the second part, which is the flow matching. And in general, let's just conceptualize it as a general algorithm to create images based on text prompts. And I will now quickly walk through the basics of flow matching, because I actually think it's a very beautiful approach. It's super simple and it's very scalable. In general, the common goal of all flow matching methods is to learn a vector field that generates a path between two distributions. So one of these distributions is often a very simple and tractable distribution, such as our standard normal distribution. And the other one is a highly complex one that we typically don't know, such as the data distribution of natural images. And after training a neural network that parameterizes a vector field, we are able to transform samples from that standard normal distribution into samples from the image data distribution by just numerically integrating this learned vector field. And if we put this a bit differently, the vector field represented by the neural network provides a way to translate a sample from the standard normal distribution into that, or into a real image. And just this general class of diffusion/flow algorithms has evolved quite a bit in the past, actually. I just want to show this here because I think we have arrived at a formalism which is quite beautiful in comparison to what we had before. That being said, all the stuff before was also quite nice. But I think, yeah, we have been able to actually, as a research community, simplify this by quite a bit. So the actual first paper on diffusion models in the modern sense was published in 2015, called Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics, and really was more like a hierarchical variational autoencoder. And yeah, kind of motivated the objective from that perspective. This then evolved into the very famous paper published by Jonathan Ho and his colleagues called Denoising Diffusion Probabilistic Models, DDPM, with the famous L-simple objective on just noise prediction. And at the same time, we also had a paper from Yang Song called Score-Based Generative Modeling through Stochastic Differential Equations, which basically described the same process through a stochastic differential equation framework. By that, diffusion really took off and evolved into a lot of different flavors, like described in this also very beautiful paper on elucidating the science space of diffusion-based generative models, published by NVIDIA 2 years ago. But what we see already is that, yeah, there was quite a zoo of different methods. And at some point, it was really unclear which one is actually the preferable one. Nobody really ran like a large-scale ablation study on all of these different methods to figure out which one is actually the most scalable, which one is actually the best for, let's say, large-scale text-to-image synthesis. And this is what also prompted us at some point to look into flow matching, which emerged as like one alternative and looked conceptually much simpler. And to understand flow matching, recall that the goal of it is to learn a vector field, again, that we represent by neural network, which provides a way to translate a sample from the standard normal into distribution of real images. To learn this vector field, we start by defining a forward process. This is very similar to standard diffusion models that specifies a path between two samples from the two distributions. We can actually recover a lot of the classic and more famous diffusion formalisms by choosing these coefficients here accordingly. So we can recover DDPM and EDPM just by choosing AT and BT accordingly. And there's a good paper that kind of outlines all of these connections, which was published, I think, 1.5 years ago, called Understanding Diffusion Objectives as the Elbow with Simple Data Augmentation, which I can highly recommend for anyone interested in the theoretical connections. And among like these different formulations, one is, I would say, arguably the most simple, which is basically just an interpolation between data and noise. And this one also leads to a surprisingly simple loss, which makes the overall formulation very easy to work with. And you basically only need a few lines of code to actually implement that. So we literally just need to sample a data sample from our data distribution. We need to sample noise from a normal standard normal. We interpolate them with t between 0 and 1. We can calculate the target as the difference between noise and data, and then regress that target with a neural network that is conditioned on the noisy version of the data that we have obtained through the interpolation and the t that we have sampled. And then at inference, after training, we can basically just integrate the equation here on the bottom by running something as simple as a standard Euler. This literally, like, you need like 10 lines of code to implement that, which is, I think, really nice, especially after looking into all these different diffusion formalisms that we had in the beginning when this stuff popped up. But of course, you can start to engineer your way into, I would say, a bit more complicated formalisms that might actually also work a little bit better. So one key observation that we made in this paper we published a year ago called Scaling Rectified Flow Transformers for High Resolution Image Synthesis was that if you sample the interpolation factor T from a uniform distribution, you actually end up with something that is very likely suboptimal, because at the two extreme cases, so either T equals 0 or T equals 1, the task that you teach the neural network becomes trivial. You either predict the data mean or the noise mean. And that kind of motivated us to look for distributions over these time steps which downweigh the two extreme cases. And then one very natural choice that popped up is the so-called log-normal distribution, which looks like this here as demonstrated on the slide, which basically naturally models this behavior. And you can then use this distribution to parameterize where you sample the time steps from, and can shift the sampling towards higher or lower noise scales, which is something which you can empirically, through a bunch of ablation studies, figure out what works best for your given training algorithm. Another aspect which is also pretty important when you actually want to generate samples with these models once you trained them, is that you typically in your data set have images of varying resolutions, and you want your algorithm or your model to be applicable in all of those. And you also want to be able to generate higher resolution images. And then there's a lot of literature on what you need to do to actually train diffusion models or related models like flow models on high resolution images. The bottom line is that for a larger resolution image, you actually need to relatively add more noise to remove information from that image, which in turn also means that when you want to sample from these models, you should probably spend more time on the higher noise levels than on the lower noise levels. So a uniformly spaced Euler is very likely not the optimal approach. And you can improve the sampling performance by shifting the noise schedule according to dimensionality of the data that you want to sample. There's a paper that I can recommend on this called Simple Diffusion. And we have also looked at this for flow matching in our Scaling Rectified Flow model paper. And the bottom line is that you can find a shifting formula which basically tells you how to shift your time steps depending on the sequence length that you want to sample at, if you have a reference sequence length n. And we can visualize what this means in a qualitative way. So if you don't do any shifting, you just treat m and n as equal, you see that the images look kind of undersaturated and a little bit outwashed. And then if you adapt that factor accordingly, you actually get saturated images, which look much better. And something that we did when we developed Flux is we actually unified these two things. So one is training time sampling, which I talked about earlier, with like the two extreme cases of the interpolation trajectory. The other, the inference time shifting into a single framework. And the key observation here is that for a flow matching model, specifically a rectified flow matching model, your signal to noise ratio is basically just -2 times the logit of t, where t is from 0 to 1. And we can use that if we sample that t from that logit normal distribution that I mentioned earlier to derive a general shifting formula for the signal to noise ratio, which is parameterized only by sigma and mu, which are the parameters of the logit normal distribution. And yeah, we can use that to derive a shifting formula for the time steps that we can use both at training and at inference, and again simplifies a lot of things. We do hope to put this stuff into a technical report very soon. We actually promised it a few months ago already. I hope that we find the time to put this out this spring, actually. Yes, but besides these kind of theoretical innovations, there's also a lot of practical stuff that you need to get right if you actually want to train these models at scale. So one key aspect that we found you need to do is when you want to train, especially at lower precisions like BF16, is a trick that was first introduced in classic vision transformer literature, which is called QK normalization, where you basically, before the attention operation, normalize your Q and K values with a layer norm or an RMS norm. And yeah, we realized that if you don't do that, you typically end up with divergences at some point in the training. And if you do it, you actually get stable results. And yeah, equipped with stable training and a scalable algorithm, you can actually arrive at scaling laws or scaling behavior for predictable scaling behavior for flow matching and diffusion models. And yeah, this is again from this paper called Scaling Rectified Flow Transformers from last year. And what we did here is we looked at the validation loss, which we averaged at fixed noise levels. So one typical thing that you see is when you start training diffusion models or flow models is that because you're in a mini batch, you typically average across like random noise levels, you have very noisy signal. You can get a clean signal by fixing the time steps at which you evaluate your training loss. And when you do that and you train a few models with different scales, you actually get plots that look very much like very familiar scaling plots from the language literature. And of course, the next question then is, does this validation loss actually tell me something about model performance? Because in the end, we are interested in sample quality, especially for text-to-image models, which is not the loss, but rather the performance after sampling the model through a given trajectory. And this is why we try to relate the model performance as evaluated by automatic metrics and human preference to the validation loss. And then we actually found very strong correlation, which is, I would say, a pretty strong signal that the scaling is indeed very predictive. And then in practice, another thing that you really want to do before you release a model is called preference optimization. This is again like very similar as methods found in the large language model literature, where you basically can also differentiate between pre and post training. Post training in diffusion world is not yet quite as evolved as in the language modeling world, but also includes a lot of early works on preference optimization. Something that works well is called diffusion DPO. And for that, you basically take a trained model, and let's consider a text-to-image model here, and given a prompt, generate different images with, for example, different random seeds. And then you have human evaluators rate these outcomes, basically have a winner and a loser of a given for a given prompt. You can collect a data set like this and then utilize this method here that was published, I think, 2 years ago, called diffusion model alignment using direct preference optimization. And this basically is a simple loss that pushes the model towards favoring the winning samples over the losing samples while staying in proximity to the teacher model, which is the model pre-DPO training. And this method really boosts final model performance quite a bit. We have found that it improves spelling and overall image quality as rated by human observers when you run a larger study. This stuff is all still like fairly, I would say, general and applicable to a lot of like different flow and diffusion models. I wanted to quickly also talk about Flux and the stuff that we did there to improve the model performance. So one aspect is in the architecture, which is one in the diffusion transformer blocks that we used as part of the architecture. We introduced something called parallel attention. We actually only introduced it to diffusion transformers because it existed already in, again, the classic vision transformer literature. And this operation basically parallelizes the otherwise sequential attention and MLP operation that you have in these transformer blocks. So in a classic block, you first compute the attention, have a residual connection, and then afterwards compute with your MLP the output of that pointwise operation, add that to the output of the attention operation. In the parallel block or implementation, you do both at the same time. And the main advantage here is that you can fuse this operation into a single large matrix multiplication, which for the modern hardware really makes the whole operation more efficient. The second part is that we again looked at the language model literature and found rope embeddings. Rope embeddings are relative positional embeddings. Before that, the most common used positional embeddings for diffusion models or diffusion transformers, flow transformers, were fixed positional embeddings, or you basically had a grid from which you were kind of taking the subgrid that corresponded to the image resolution at which you were sampling. So we also introduced this row positional embedding, which gives the model basically a continuous flexibility in what kind of aspect ratios and resolutions it can generate, and overall also improve the performance. And these ingredients, then flow matching plus these architectural innovations, contributed to our first flagship model, which is Flux 1. And Flux 1, we actually released in different flavors. So Flux 1 Pro is our proprietary model, which runs behind the BFL API. We also released a open weights model, Flux Dev, which was the one from the plots from Hugging Face, which I showed earlier. And then we also released a completely Apache 2.0 open source model called Flux Schnell. And these models basically differentiate by the amount of distillation that we used to make the open source versions more efficient. For Flux Dev, we only used, we did not distill the steps. And for Flux Schnell, we distilled the dev model into a 4-step model. But then I want to talk a little bit more about this distillation procedure, because actually if you generate an image with a standard flow or diffusion model, you have to wait for quite a while, which can be painfully slow. So there's a lot of different methods on diffusion distillation, flow matching distillation. I want to briefly talk about adversarial distillation, which we found to work pretty well, especially in the regime of very few steps when you really want to squeeze out the juice of these models. In this paper, which we published over a year ago now, we first looked at how we can combine adversarial training and diffusion models. And this was actually motivated by, I would say, a failure, where we tried to scale up classic GAN training, like style GAN T, which my colleague Axel was working on previously, to text to image, high resolution application, but the results after a lot of pain were still looking not really good. And then, yeah, we looked at like related methods that at the time were published for diffusion models, like one-step latent consistency models. This one here was being trained on Stable Diffusion XL. And if you look at these like one-step outputs, they kind of remind you on, or kind of look similar to autoencoder outputs if you don't have a adversarial objective on the reconstruction. So they might just need a little push to the manifold of real images. Of course, this is an overall simplified picture, but can serve as a motivation of why you actually want to combine these two things. So we ended up trying out this method called ADD, Adversarial Diffusion Distillation, where we basically combine a classic distillation approach where we match the outputs of a TUM model, pre-trained diffusion model, and an adversarial loss. And if we train that, we see that for one steps, we can actually arrive at crisp samples. And yeah, when I first kind of interactively sampled the model, I found these results pretty insane because you can really type and see the image change at the same time. There's a little bit of a trade-off that you end up having when you use this method, which is a classic quality diversity trade-off. So, for example, here we used SXL as a teacher model, and you can see that like for a given prompt, there's a lot of variability in the outputs and poses, and you don't have that anymore after the adversarial distillation. The nice part is that you're actually able to improve in visual quality over the base model because you have that added adversarial component in the overall training pipeline. And yeah, as I said, this enables like interactive applications. I like this one here at the time by Kriya AI, which is you can basically drag around a sketch and then use image to image to map this into a real image. And it all happens in real time because the model is so fast. The problem with that approach is that it's not really scalable because with this first iteration, we actually decoded back into pixel space, used a Dino V2 discriminator, which is also fixed to a certain resolution, doesn't really have multi-aspect support, and most importantly, that this like and encoding into pixel space and then back again into latent space is just way too expensive. So this model or like this approach quickly hit some limits, especially for high resolution outputs. Was also one reason why we only were able to generate 512 by 512 images with the first iteration. And this is what we try to fix with the second approach called latent adversarial diffusion distillation, which basically simplifies the whole pipeline by also starting from a pre-trained diffusion model as a teacher, and then using some of the teacher features in the latent space of the or some of the pre-trained teacher features to actually train a discriminator on top, all in the latent space. And this means that we have all the flexibility of the teacher model. If the teacher model is flexible in output resolutions, the student model automatically is as well. And we also save the very expensive decoding space into pixels, decoding step into pixel space. And this then in turn also means that we can just scale to much larger models. And yeah, if we look again at like this plot that I made or talked about earlier with the mode seeking and mode covering models, we can basically distinguish two kind of, or we can identify two kind of modeling schemes, right? One is the pre-training or the scaling regime, which is basically something we can cover with latent flow matching or latent diffusion or autoregression. And then the other one, the entropy removing one, or the realism prior one, is something that we use both in the autoencoder stage and then also in the distillation stage. And yeah, this is why I think that these hybrid models currently really make sense and work the best. It's something that we also unified in this like update to Flux, which we call Flux 1.1 Pro, which both improved the model quality and the actual iteration speed. Yeah, it's basically a combination of all these different things that we talked about here. Here's some samples. We can skip those. In the interest of time, I will also skip talking about 4K outputs. And then, yeah, maybe quickly, you can also standard practice now, take like a pre-trained model and turn it into a bunch of like different and interesting applications, like an in-painting model. We released that as Flux Fill. So we can take a text prompt and an input image and actually modify that additionally based on a mask. So where you want to change, like, or where you give a certain region of the image that you want to change, you can use the same mechanism to enlarge the given image. You can do this iteratively. You can also use that for like iterative workflows where you start with, let's say, this blank room here, and then you add certain components and make it a much more comfortable living room. You can turn this model into a retexturing model by conditioning it on structural information such as depth maps or Kenny edge maps. And also make an image variation model out of it, something we released as Flux Redux, where you basically take an input image plus a text prompt and can combine them into interesting new outputs. I want to talk a little bit before we end about like something that I find very, very exciting moving forward, which is the customization potential that we have with generative models. This is something that we have released recently, which is basically a fine-tuning API. And here you just need a few images, like 5 to 10, of the same concept. And then you're able to fine-tune this based on a few data points into a base model, which before that actually doesn't really know anything about that concept. For this demo here, we actually walked around our office and put this stickers everywhere, took a data set, and fine-tune the model, which gives pretty good results. And yeah, you can do that with, I don't know, custom characters, like this dog, which the model didn't know before, or clothing or certain styles, and even combine these. But I think the most interesting aspect about this is that currently, I would say this takes too long. What you want to do is you want to skip the fine-tuning step, because this like 5 to 10 minutes of waiting, or like even more, to obtain a result is something that I would say is not ideal. So one very interesting direction of model development is, in my opinion, this whole text-based image editing, zero-shot personalization, as we have seen in a very nice paper called Omnigen, and also in a first demo of Gemini 2, which included a native image generation. And what you can basically do is you can take an input image, you can use a text prompt, and try to modify the subject or the object in the input image. And yeah, this is another example for that, where you basically take the input image here on the left and then prompt the subject's eyes are now open, subject is looking directly at the camera, the subject's hand is holding her hair, smile is wider, etc. And it actually does that in the generation. And I find this very nice because you can really skip the fine-tuning stage and basically enable iterative application on every piece of content that you have. It's also something that when you actually want to generate an image or video later on, and you don't like the input, the output, you typically go back to the text prompt stage. You refine your text prompts, then you regenerate. But then a lot of other stuff changes in the same image. And that's ideally something that you would want to avoid. Yeah, second big aspect, I think, for the future is video generation. We do have a bunch of nice models out there already. I think the next big steps are really around like basically streaming from these models. So I want to be able to generate the next 10 seconds of the video while watching the first 10 seconds. I want to have it like more controllable beyond, I would say, just image to video. So ideally, we can disentangle camera and text prompting. And also something that a lot of the models currently also struggle with is generalization to basically arbitrary styles and inputs. And the last kind of classes of applications that I'm personally also extremely excited about is 2D scene generation. There's a few demos out there that kind of hint at the potential of this technology. Here's one from World Labs, which they've released on their blog post. Basically takes this input image on the left and then turns this into an interactive 3D scene. Or another one, which I really, really like, Genie 2 from Google, which is basically able to generate playable worlds, and you can interact with your keys to walk through that playable world. Oh, there is a very important disclaimer, which is they are generated by an undistilled base model to basically show what's possible. So this is not yet real time, but I think if you look at the really fast evolution of generative models that we have seen in the past, and combine this with like this direction that we see here, you can very much imagine like how this will look like in a few years. And I find this extremely exciting, and potentially opens a whole new world of maybe even media consumption ways. I wanted to end with a few just general learnings that we had at our startup that might be a little bit different from classic academia. So obviously the first and most important one is that scaling really matters. So the goal in the end is to make a model that works well and that can be served at scale. And to that end, you kind of have to go much further than just demonstrating that the idea works in practice. Really make sure that your distillation works at a high quality. In general, you always struggle with like higher failure rates for large runs, just because in a distributed setup, the chance that a single GPU in your training setup fails is just higher if you use more of them. A very important part, which I would highly recommend to everyone who is kind of interested in scaling up models, which I found to be skipped over quite a bit, is like on just parallelization methods for making the training more efficient. The standard paper that I would recommend on this is the Zero paper, which was already published in 2019. I also didn't know about this for quite a while, actually. It's basically a foundation for a lot of like advanced sharding methods such as FSDP, and then there's also a lot of like work around tensor parallelism, context parallelism, etc. And I would say the overall goals are very similar as with academia. You want to achieve a state-of-the-art model. However, how you measure that can be very tricky because if you actually run, for example, an API that is served in like different applications, it really matters like what the application actually looks like. So maybe your model is being viewed at on a screen or sampled on a like phone screen or on a high resolution 4K screen, and basically that already makes a huge or has a huge impact on the actual evaluation of your model, and nobody really cares about an FID score or something like that. And in general, yeah, I would say the simpler the method, the better, because just makes it easier to figure out bugs and enable scaling in the end. That's it so far. There's an overview of a bunch of resources that we that are public, where you can play with the models, where you can download models on GitHub, Hugging Face, or also some interfaces that actually integrate these models if you want to play with them. Big shout out to the whole team. Without that team, it wouldn't be possible to serve these models and to make these models. And yeah, thanks for your attention.
Cool, great. Thanks for the very interesting talk. Unfortunately, Matthias had to run, so I'll be helping to moderate any questions. So if there are any questions in Zoom, please just unmute yourself and ask, and anybody on YouTube can ask in the chat. All right, maybe I can also start here. So the results that you show look pretty amazing, right, from just an image quality perspective. And you also mentioned kind of the trade-off between these like mode seeking or mode covering kind of models. Is that still something that you try to tackle? Because, I mean, obviously you guys are training on massive quantities of images and visual data, but stuff that's typically readily available on the internet is still fairly biased to a degree. And so are you trying to also cover other modes that are, you know, less common than the standard, maybe sort of Instagram style of content? We also are interested in generating things like, you know, robotic interactions and stuff like this, which is not really commonly captured in standard, you know, phone camera kind of setups.
Yeah, 100%. Maybe just to clarify, I think when I talk about mode covering versus mode seeking, I really mean it more in a like in a bit more abstract way, where it's mostly about like these imperceptible details that are present in natural data. So not really about like the high level concepts that I would say are, I don't know, maybe like different cultures have different concepts, for example. That being said, I think this is obviously this is super important. And actually, yeah, there's an interesting combination of like the pre-training algorithms, and then also the preference training algorithms at play. Especially the preference tuning can have like a huge impact, and there it actually, like what I said earlier, when you it really matters how you evaluate the model, what kind of application you actually use to view the samples from the models, to rate the samples, because that can also introduce some kind of artifacts, sometimes very like on smaller screens, or if you look at a lot of samples at the same time, then you might lose a lot of detail. And then, of course, it also depends on the audience that does the rating for you. So yeah, there's a lot of like complexity at play, but definitely, since we also want to have our models being used everywhere, we are definitely working on that.
Okay, there's also a question on YouTube. When one interpolates between two latent embeddings, we can expect different interpolative synthesis when using different VQ, VAE, or other sort of VAE architecture designs. can you speak to the connection between the VAE design and its impact on hallucination or generalization?
Yes, that's a very good question. And I think, yeah, I think the most important aspect for a given VAE design is probably how you structure your latent space. So you can basically tune the compression factor by tuning the dimensionality of your latents that the encoder produces. And then if you run a study on this, you actually find that as expected, you can increase the reconstruction quality by just increasing the dimensionality of the latents, basically reducing the bottleneck size of the whole pipeline. But learning with a generative model these higher dimensional latents is not as trivial, and you need to scale up quite a bit to actually make up for the additional complexity that higher dimensional latents introduce. So what that means is that you have to find a sweet spot between the compression factor, the reconstruction quality, and the trainability actually of your generative model. That trainability generally increases when you scale up the compute that you put into the generative model.
I would have one question as well. So thanks for the amazing talk. I have a more abstract question for diffusion and flow matching versus autoregressive models for image generation. So I was recently interested in this other paradigm of generating images as an autoregressive sequence. Is this something that you have an opinion on in general compared to diffusion or flow matching?
An opinion, yes. And I think it's a complex question. It's actually not 100% clear which one is in the end the more efficient one, right? We have a lot of like optimization currently happening for pure autoregressive models. There's even like dedicated hardware being built. So that might be an argument actually in favor of autoregressive models. On the other hand, you have a bunch of arguments that are in favor of diffusion models. You can achieve like the same or better performance with much smaller diffusion models than you can with autoregressive models. You can distill them into very few steps models. With an autoregressive model, you always have to synthesize the full sequence. And you rather have to do like the model distillation, like make the model smaller route instead of only doing step size reduction. And finally, I think it's also a little bit unnatural to model 2D images as a 1D sequence. But yeah, no very like super clear opinion actually. There's also very interesting hybrid approaches. Like I think one is called transfusion that basically combines both and trains an autoregressive text model with a diffusion image model at the same time. There's also approaches that start from a pre-trained autoregressive model and then turn that into a diffusion model. So I think we'll have to see which one will actually win, if at all.
Okay, yeah, thanks.
Well, so speaking of unnatural, it's also not that natural to model an image by a series or just a few kind of denoising steps, or if you consider natural as how people typically design images, right? And this has historically kind of been the way that the image generation was attempted to be designed for a fair bit of time before recent developments. So do you think there's still like a role for embedding more sort of knowledge and structure into the latent encodings?
I don't know. That's a really tricky question. I would say from everything we've seen so far, everything points at no. You just want to have it as flexible as possible and as general as possible. and maybe just end up with this new paradigm, which, yeah, is not resembling how a human maybe generates like a piece of content, but maybe that's also not super important. There's like also these like very interesting connections between diffusion and autoregression models when you look at diffusion as autoregression in frequency space, and that I would say is actually a bit more of a natural approach. So yeah, I in general, I think incorporating these priors, especially for these like very large scale tasks like pure image generation or even video generation, where you have an abundance of data, is probably not going to succeed. But maybe for more specialized tasks, or if you really want like efficiency in certain domains.
Fair enough. All right. I think we're a little over time on the stream, so I'm gonna go ahead and end the stream now.